Welcome to the review on Unit 7, which is going to make you want to jump up and down because this unit is about oscillation. There are 5 different sections for this. We're going to define a special type of oscillation called simple harmonic motion. We're going to look at the frequency and period and angular frequency of all oscillating objects. We're going to look at how to represent and analyze simple harmonic motion energy for things that are moving back and forth, or simple harmonic oscillators, and we'll look at the simple and physical pendulums. So first thing we're going to look at is defining simple harmonic motion. Simple harmonic motion is going to be a special type of oscillation, which is going to be any back and forth motion is an oscillation. Simple harmonic motion is a special type of that where the restoring force is directly proportional to x. You can see that down the bottom. So let's back up and first talk about what a restoring force is, and then we'll see what we mean by it's directly proportional to x. So restoring force is going to be the force that anything that's moving back and forth needs to have, because it's the force that's going to point towards the middle or the equilibrium position when you displace it to one side or the other. So it's always going to point opposite the way that the object is displaced from equilibrium. So for example, in a mass spring system, when the spring is at equilibrium, then if we stretch it or compress it to either side, the spring force is going to exert a net force. And if it's flat, that Kx is the net force. That's why we have it set equal to ma. And that Kx is the restoring force in this problem. For a vertically hanging spring, again, there's a spring, but there's also gravity, so the equilibrium is going to be when those two forces are balanced, and any force, any time that the mass is going to be stretched out or compressed, then that is going to exert a net force, which we can find by doing Kx minus mg. So Kx minus mg is our restoring force. For a simple pendulum, simple pendulums have the mass located on the very end of the string. The force that points tangent is the restoring force because it's pointing down towards the vertical hanging position, which is our equilibrium position. So if we displace it to the left or to the right, the tangent pointing force, mg sine theta, is our restoring force. For a physical pendulum, that's when you have a rotating object as the pendulum instead of a point mass moving in a circle. We'd have to do torque on this since it's a rotating object, and the restoring torque in this problem would be the gravity's torque, which is mg times the distance from the pivot to where the force is acting, times the sine of the angle between those two arrows. That would be the restoring torque. Now, if we look at these cases, simple harmonic motion would mean the restoring force is directly proportional to x, or if it's a restoring torque, as the case with physical pendulums, it would be directly proportional to theta. So here we have Kx is directly proportional to x, and this is simple harmonic motion. Over here where we have gravity involved, it's still a linear relationship with x, and it's still simple harmonic motion. Pendulums technically are not simple harmonic motion because they do not have a direct dependence on x for simple pendulums, and they do not have a direct dependence with theta with physical pendulums. However, as you'll see in Unit 7.5 when we derive these period equations, we will have to apply what's called a small angle approximation. So at small angles, these can be modeled as simple harmonic oscillators. So typically in AP, we're only going to be using these small angles, and that therefore these can be modeled as being simple harmonic motion. Let's take a look at a quick multiple choice example. In this case, I'll paraphrase the text. It's going to have a car that's going to be released, it's going to fall down, and it's going to bounce back up off this spring. And it says, although the cart's motion is periodic, meaning it's oscillating, it's not simple harmonic motion. And which of the following is the justification for this claim? And so as we're looking at this, we'll do process of elimination. There's no equilibrium position where the net force of the cart is 0. So is there no equilibrium position? That's not true. There's going to be one right down here where the mg sine theta downhill component is equal to the spring force back up. So at some compression, there will be an equilibrium position. So A is not correct. B says there is an equilibrium position, but the spring is not at its relaxed length when the cart is in equilibrium. That is correct. However, that's not a reason why this is not simple harmonic motion. It has nothing to do with that. That's just simply a statement about the forces, and in particular, its equilibrium position. C says there is an equilibrium position, but there's no restoring force towards equilibrium when the cart is not touching the spring. So the spring can act, right, as a restoring force that is directly proportional to x, and therefore would be simple harmonic motion. However, when it leaves contact with the spring, there is no more spring force, and therefore there's no more restoring force that's directly proportional to x. However, there is still restoring force because the mg sine theta, just like a pendulum, is going to try and restore it back down towards that equilibrium. It's going to slow it down and then speed it back up on the way down. So this is not correct because, yes, there's an equilibrium position, but there is still a restoring force, mg sine theta, while it's on the ramp and not touching the spring. D is going to be the correct answer here, so it says there is an equilibrium position and a restoring force on both sides of the equilibrium, but the restoring force is not proportional to the cart's displacement from equilibrium when it's not touching the spring. So D would be the correct answer here. In 7.2, we're going to be looking at frequency, period, and I'm also going to put angular frequency into the mix here, as these are all three sides of the same coin, assuming we had a three-sided coin, meaning if you know one of these values, you can directly calculate the other quantity. So for example, if we knew period, because that's an easy one to get off a graph, we know from pre-calculus and doing these periodic functions or sinusoidal graphs, these sine waves, we can get the period by just doing one cycle on the graph. And that's going to be the seconds, assuming time is on the x-axis, for one cycle. And with that, then I could just do the inverse to get the frequency, because we're going from seconds per cycle to cycles per second. So that would be an inverse. We're going to often need to use angular frequency instead of good old frequency because of the calculators and the cosine functions and things that we have, such as this one down here. So we're going to need to convert the frequency into, instead of cycles per second, we're going to need radians per second. And so if we just use the idea that one cycle is modeled as 2 pi radians, one full time around a circle, then we could just use this equation where omega would be equal to 2 pi times then whatever the frequency is. Or if we wanted to put it in terms of period, it would be 2 pi over the period. We know from pre-calculus that the period is 2 pi over b. It should be noteworthy here that b in pre-calculus is the same variable as what we're going to refer to as omega, which has the term angular frequency because of its angular units of radians. The period of different simple harmonic oscillators are going to be used frequently throughout Unit 7 problems. And you can see that these equations are the equations for the three different simple harmonic oscillators that are common in APC. So one would be for a spring, doesn't matter if it's horizontal or vertical. This is the period of a spring. It should be also of note that we're going to derive these in 7.5. So we can check out the later part of the video in 7.5 to see these derivations. Simple pendulum, physical pendulum, and that would correspond if we used our period as 2 pi over the angular frequency relationship. Then we could also express omega in terms of these similar quantities. In 7.3, we're going to be looking at representations and analysis of simple harmonic motion. So let's take a look at graphs and functions. The graph we already talked about briefly, and we said that, from pre-calculus, we could get the period, which would be the time it takes for one cycle. In this case, I've shown trough to trough. We could also use crest to crest. Or if we use where it crosses the midline or sinusoidal axis, we'd have to find the next time it's on its way down like this, which would be over here. Basically just one cycle, and the width of that along the x-axis would give us then seconds per cycle. Amplitude should be okay on this one. We are responsible for also knowing velocity time graphs, acceleration time graphs, and even kinetic energy or potential energy plotted on the y-axis. So any of these that are going to have these cosine and sine functions, but really all of them are predicated off of the three kinematic ones, which would be position, velocity, and acceleration. So for example, kinetic energy would be associated with velocity, whereas force would be associated with acceleration. So they would have the same cosine or sine shape. So let's look at those kinematic relationships of position time, velocity time, and acceleration time. If we start off with the position time graph, I was calling this x, but we could also model it as y. Then we have a period, so we have a frequency, and if you can see right here, that frequency can be turned into omega. That's going to be used for our cosine function. If we take a derivative of that, we would get velocity, and you can see the derivative of that. Now it's important to note here that this is the maximum velocity, right? Just as A is the maximum position from equilibrium. So therefore, we now have an equation that we can memorize for the maximum speed. So absolute value of this would give me then omega times amplitude. So that's a way of quantifying or calculating the maximum speed in terms of these angular variables, oscillatory variables, omega and amplitude. This is useful if we not only just want to get the maximum speed, but let's say you wanted to determine the maximum kinetic energy. If we had omega and amplitude, we could solve for the maximum speed and then get the kinetic energy using our kinetic energy equation, 1/2 mv squared. If we take a derivative of the velocity one, so now two derivatives, our second derivative from the position time function, we're back to cosine, but now we have negative omega squared a. And again, just like with velocity, this represents the maximum acceleration, which we can memorize as a quick access way to get to the maximum acceleration. This is not only useful for getting the maximum acceleration, but also the maximum force. The maximum force is what we use a lot in these, and in particular for deriving those period equations that we mentioned earlier that we'll show you again at the end of this video in 7.5. So we'll come back to this Amax at the end of the video, so check that out please at the end. Also, in particular with that max acceleration that's useful, since we often do forces, as I said, one variation of that is writing but do not solve a differential equation. So you may be given an equation that is a Newton's second law, meaning like forces equals ma, and they'll replace a with its differential, and that differential is going to be written as a second derivative of position. So if we get rid of a being the max for amplitude, and then a over here for acceleration being its max, then an instantaneous acceleration would depend on your instantaneous displacement, which if we wanted to for some reason write that as a differential equation, we could just replace the a with the second derivative position. We're using the second derivative position here because it's written as a function of x, so we want our differential to be written in terms of x as well. We will never be solving these within the boundaries of the AP Physics C curriculum. So here's an example of one. You can see this gives us this equation. So they're giving us ma and then equal to some function defining the force. So this is the force. I can't highlight it. Beta, quantity x minus x naught, is the net force, which is set equal to ma. And they've replaced this a variable with the differential. That allows this to be in terms of, the differential to be in terms of x and t. And our forces also depend on x. Notice here they don't ask you to solve for it, they just ask you to analyze it. So we should be able to recognize that this is just simply acceleration, and we should be able to substitute it out if we want to write a differential equation but not solve it. Please check out the last example of this video, which is called a torsional pendulum, and you'll see an example of us writing but not solving a differential equation. In 7.4, we get focused on the energy of simple harmonic oscillators. Very, very common in the AP Physics C curriculum to deal with energy. Luckily for us, the majority of these energy problems are just simply conservation of energy applied to an object that's moving back and forth. Springs, for example, you have potential energy of a spring, and you have the kinetic energy. If it's on an incline or vertically hanging spring, then we also have gravitational energy to account for, which just adds an extra layer of complexity to have to deal with. Ultimately, we're just going to use our conservation of energy statement. Please write this out. According to the chief reader of AP Physics C, there's a good discrepancy between students that wrote this out and students who didn't in terms of their success in answering the questions correctly. So we want to write this out and then slash out the energies that aren't there. Helps us to stay organized and inventory what energies are present more accurately. One key that is distinct to oscillation in Unit 7 that we ought to make sure we're comfortable with is the maximum speed, Vmax equals omega a, is always going to occur at equilibrium position. This makes sense because if there's a net force, we're either slowing down and we're at a maximum speed, or we're speeding up and we haven't reached the maximum speed yet. So the equilibrium position is going to be the just right position. In an energy perspective, we don't have any other types of energies. We don't have a potential energy at equilibrium because we don't have a spring that's stretched or compressed. And for pendulums, we don't have a height if we're at equilibrium. We're at the bottom there. So that would represent when all the total energy is in kinetic. So for oscillation, that equilibrium position is always the sinusoidal axis or the middle of the motion. In 7.5, we're going to be looking at simple and physical pendulums. So we're going to most often apply forces to this. To derive these equations, you can use energy, but the math is a little bit more complicated with it. It's just more tedious algebra, but it is accurate and okay to do. We're going to look at forces when we derive these. It's more straightforward and more typical to what you'll see in AP Physics C. General way that we're going to be approaching deriving these period equations that you should be able to do in APC is we're going to apply the restoring force, meaning treat it like a force problem, when at its maximum acceleration, meaning maximum displacement from equilibrium. We're going to move as far as we can to the side. Usually that's the release point. And since we have a force net equal to ma, our restoring force is equal to ma, and we have a definition of A max in terms of that omega in amplitude, that omega is going to be the key then to getting to period, right? As we recall, omega is equal to 2 pi over the period. So these equations are what we should be able to derive. We'll come back to physical pendulums here in a moment, but mass spring and simple pendulums both are going to use the same idea, and that would be forces. Physical pendulums would use the same idea, but it's torque. So it's a little more complicated. Torsional pendulums also use the concept of a restoring torque. So let's take a look at one of these examples. Mass on a spring is the most straightforward here. And so we're going to be using forces. Again, the restoring force at its maximum displacement, meaning at its amplitude, is going to then be equal to ma. I'm taking this as an absolute value or magnitude. And I'm going to sub in the omega squared times amplitude in for A. That brings omega into the mix, which ultimately I'm going to try to solve for so I can get to period. In this case, it's a pretty straightforward calculation to get that 2 pi root m over k. Same logic for our simple pendulum. A little bit more complicated because our restoring force of mg sine theta when set equal to ma. It's a little more confusing because we don't know what A is. So A is going to be this arc length. Arc length is equal then to the radius, which is L times theta, right? Arc length is S equals R theta. So this blue highlighted arc is our amplitude, and we could set that equal to L theta. If L theta is our amplitude, it doesn't divide out with sine theta. However, if we apply a small angle approximation, then we can, in fact, divide out the sine theta and theta, assuming that they are approximately equal to each other. The blue angles here, meaning 0 to 15 degrees, if we take the angle in radians in decimal form, and then we do sine of that angle, we can see that they're pretty close in agreement, less than 1% different, for all angles less than 15 degrees. If we keep that angle less than 30 degrees, then the difference between sine theta and theta are only 5%, and we can just use the approximation of saying essentially those are close enough that we can cancel them out. It is beyond the scope or boundaries of AP Physics C to deal with these when there isn't a small angle approximation. So we are always going to apply the small angle approximation. Another way to look at the small angle approximation that might sink in a little bit better is what we're essentially doing is we're modeling the back and forth motion as being along a flat horizontal axis. If we look at the distance of that flat horizontal axis to one side, then its amplitude is this flat yellow bottom of the right triangle, and that would be equal to L sine theta. So approximating this arc as a flat horizontal amplitude of L sine theta would allow then for the two sine thetas to divide out. AP wants you to be able to apply the small angle approximation in the way that I have noted here, but it is also equivalent to do L sine theta and then allow the sine thetas to divide out. Approximating this amplitude as L sine theta is a small angle approximation. So now we're going to get into the physical pendulum, and a physical pendulum is going to, instead of using force, we're going to use torque. So we're going to use a rotating rod of rotational inertia I. We're going to assume that it's pivoted at about a point that's a distance d away from the center of the rod. And so if we look at the torque that's going to act as the restoring torque when we displace it to either side, that's going to be equal to our force mg times the distance that force is from the pivot times the sine of the angle between. I'm not crossing that out because it's not there. I'm crossing it out here in a later step. I'm going to set this entire restoring torque equal to I alpha, and again we're going to then substitute out that angular acceleration with the oscillation equation for it. We haven't really looked at this one specifically, and in terms of alpha, we've used it in terms of linear acceleration, and it's the same thing except we're going to be replacing the linear acceleration and linear displacement with the angular terms, so angular acceleration and angular displacement. In doing that, we're going to apply that same small angle approximation that allows us to divide sine theta with theta if they are essentially the same value. That allows us then to calculate the period of a physical pendulum. The only real complications we have with this kind of a problem, if you ever see a physical pendulum, would be different values for d or different objects that are rotating. It might be a system of different objects glued together that we have to calculate an I value and proceed on. So now that we've derived all three of these, we can take a look at this, which is noting that the physical pendulums often require you to determine rotational inertia I and distance d from the pivot to the pendulum center of mass. That's going to be an important thing to recognize as you do some of these problems. That usually is where people get stuck, not so much that it's a physical pendulum. A torsional pendulum is also something that can be on the AP exam, and that's going to be a way for them to give you a function for the restoring torque and have you apply the same logic that you would to a physical pendulum, but with a different restoring torque than the one we had here, mgd sine theta. So let's look at a quick example of that. In this problem from the 2011 exam, we have a torsional pendulum, which is a disc that's flat, and then it has this cord here, or a flexible rod as they call it, that twists, and as you keep twisting it and twisting it and twisting it, then when you release it, it slowly starts to unwind more and more and more and more and more, and then it overshoots and starts to wind up the other way, and then it comes back, and so this is going to twist. The torque due to that twisted flexible rod is given here as negative beta theta. Since they're giving us this function, we're going to use that as a restoring torque instead of the mgd sine theta that we did for a physical pendulum. Notice here in A it says, in terms of the quantities given above, write but do not solve the differential equation that could be used to solve for the angular displacement as a function of time. That means that our differential has to be a derivative form of theta with respect to time. Since our function here is also in terms of that same theta, then we have to use the second derivative like we did with the second derivative of position, x in time, but with theta instead of x. We're not going to be solving this, as I said before. It is outside the bounds of our class to be solving this, but we should be able to write it. And you can see here that they do not ask us to solve it. They ask us to determine the period, to derive it, in the same way we would as a physical pendulum that required torque, but with our function here for the restoring torque that was given. Thanks, and I hope you're so excited that you want to jump up and down.